Hello guys, so in today's video we're going to discuss vector spaces and subspaces. So without further ado, let's delve right into it. So first let's look at a definition. The vector space is a non-empty set of objects called vectors on which we have two defined operations, addition and multiplication by scalars. And these 10 axioms, if they hold true for those elements, then that set is a vector space. So if you have any set of vectors and if you prove that these 10 axioms hold for that vector set of vectors, then that set is a vector space. So the axioms are basically the sum should, if there are two vectors, then their sum should also be there. The order of adding should be immaterial. Similarly, if you add two and then add the third, or first you add the second and third and then add the first, it shouldn't really matter. There should be a zero vector in V. So without the zero vector, your vector set cannot be a vector space. So if you have, say, three vectors, 1 1 1 2 and 1 3, then there is no chance of it being a vector space just by this point. So these axioms are really powerful to disprove that set is a vector space, because you can just pick any one of them which does not satisfy and you can say that this set is not a vector space. For each u, the negative u should also exist in the vector space, in the vector set, for that set to be a vector space. If there is a vector, then its scalar multiple should also be there. Then these properties, like if you multiplied the sum of two vectors with a scalar, then it should be equivalent to, first of all, multiplying the scalars with the vectors and then adding. Similarly, these properties as well. So you get a general idea. So we won't waste much time. We'll get right into the examples. The example: the space Rn where n is greater than or equal to 1 are the premier example of vector spaces. The geometric intuition developed for R3 will help you visualize. So basically, if you have this 2D plane, then all the elements in this 2D plane are in R2. So basically, this satisfies all the axioms. You have the zero vector. If you have, say, two vectors u and v, and you add them, so by parallelogram law, this is u plus v, then this is also in R2. So similarly, you can try and prove all the axioms for this vector space. Similarly, you can visualize this for R3 as well, and this visualization will help you in higher dimensions where visualization directly is not really easy. So now for example 2, if we have V be the set of all arrows here means directed line segments in three-dimensional space with two arrows regarded as equal if they have the same length and point in the same direction. And then and if we define the addition by the parallelogram rule, which was there in the book in this section, but you must be knowing the parallelogram rule for addition of vectors. And for each v in V, define Cv to be an arrow whose length is mod c times the length of the vector v pointing in the same direction and otherwise pointing in the opposite direction. Show that V is a vector space. So basically, we are given with these conditions, and we have just need to show that these conditions satisfy all those axioms, right? So V is the set of all arrows in 3D space. Then V is defined geometrically using the concept of length and direction. So we have, because they have defined them being equal only on the basis of their length and their direction. So we haven't really talked about any coordinate system here. If we have an arrow of zero length, that would really mean just having a single point and without any direction. So an arrow of zero length is a single point and it represents a zero vector. We also have, say, if we have a vector v and we multiply it with the scalar -1, so we would have a vector in the reversed direction, like here in this figure. So this basically shows that we've proven some of the identities, axioms, sorry, which are axiom 1. So axiom 1 was the sum is there. Next, we've proven axiom 4, which showed that the zero vector is there. We've proven axiom 5, axiom 6 and axiom 10 as well. Axiom 5 was the existence of the negative. Axiom 6 was the scalar, and axiom 10 was multiplying the vector with 1 really makes no difference. So uh, these axioms were verified, and the other two were verified geometrically. So for instance, we had to verify u plus v is v plus u. So we had this vector u and this vector v, and we got u plus v. However, if we move u to be on the head of we move u such that the tail of u is on the head of v, then we get v plus u as well. And we can see u plus v and v plus u are in the same direction and are of the same length, since they are opposite sides of a parallelogram, hence they are equal, because we had defined it in such a way. Similarly, if we had u plus v plus w, then here we have u, here we have v, and here we have u plus v. And similarly, when we add w, we get u plus v plus w. On the other hand, the opposite diagonal was our v plus w, and we can just add u in it, so we get u plus v plus w. So this example was a bit cumbersome, but you get the idea. Similarly, we have example 3. Let S be the space of all doubly infinite sequences of number usually written in a row rather than a column. So basically, this set, doubly infinite meaning it goes from y minus infinity to y infinity. And if we have zk being another column element of S, then the sum yk plus zk should be the sequence yk plus zk, formed by adding corresponding terms of yk and zk. So basically, say if we have yk equals 2, 3 and zk equals 3, 7, then yk plus zk is formed by adding the corresponding elements 5, 10, and this would also be present in that infinite sequence. The scalar multiple similarly will also be present, because you can just multiply, say, this by 2 here, you will get 4, 6, and that would also be present in that doubly infinite sequence. And finally, the vector space axioms are verified in the same way as for Rn. Elements of S arise in engineering. Okay, so this is just an application and we don't really have to delve that much into it. Finally, we look at the set Pn of polynomials of degree at most n. So basically, all polynomials of the form a0 plus a1t plus a2t square, so on, where it has the degree of at most n, right? So an can be 0, so it will have the degree of tn minus 1. The degree of n minus 1. If we have only elements up till t square, then it will have the degree t square, and so on. The degree of p is the highest power, and yeah, if pt is equal to a naught is not equal to 0, which basically means that if the rest of the coefficients are 0, then the degree of p is 0, right? Because this is effectively t to the 0. If all the coefficients are 0, p is called a 0 polynomial. You must be knowing this. The 0 polynomial is included in Pn even though its degree for technical reasons is not defined. This is a very important point, and you might get a question like what is the degree of a 0 polynomial, and some people might just write 0 or 1 for that matter, but the degree of a 0 polynomial is really not defined. Now if p is given by 4, like we have a polynomial given by this equation, and we take another polynomial qt which has this constants as b0, b1 and so on, then the sum of pt plus qt can also be written something like this. So basically, I won't take all the terms, but why not, let's take all the terms. So if we have at is equal to a0 plus a1t plus up till an t to the n, and we have this bt, another function, which is b0 plus b1t plus bn t to the n. I should really not name these because this might cause some confusion with the coefficients. If you add them, p plus q of t, it's effectively taking the like you took a0 plus b0 and placed them together, then you took t common from a1 plus b1 and so on up till for t to the n you took an plus you took t to the n common and made the coefficient as an plus bn, and this will also be in that vector space because this is effectively also a polynomial of degree Tn. This should have been Tn here. I made a mistake, so this should have been Tn. Yeah. Similarly, if you multiply, you'll get equivalent to scaling those vectors and so on. So if you check for all the axioms, you'll see that all the axioms are being satisfied here as well. So Pn is a vector space, and this is a very important result because this is used in lots of statistical trend analysis of data. So if someone just asks you, is the set of all polynomials of degree at most n a vector space, you can say yes. The set Pn of polynomial of degree at most n, which consists of polynomials of this form, is a vector space, and n should be greater than or equal to 0 because otherwise they are not polynomials. A polynomial cannot have a negative degree. Let's look at example 5 as well. Let V be the set of all real valued functions defined on a set D. So typically we define functions of the set of real numbers or some interval of the real line. Functions are added in the usual way. So you can add f of t plus g of t, and you'll get something, and likewise you can scale them. For instance, if d is r, so if you have the domain of the functions to be the real number system, the entire real number system, and you define the function f of t to be 1 plus sine 2t and g of t to be 2 plus 0.5t, then you can just simply add them or scale them like this. Two functions in V are equal if and only if their values are equal for all t in D. Hence the zero vector in V is the function that is identically 0. F of t is 0 for all t, and the negative of f is minus f. Yeah, axioms. So basically this was quite self-explanatory. The zero vector in V is a function that is identically 0. So if you take a zero vector, okay, I'll just give an example. If you have a zero vector, then say you write it as 0, you can also write it as 0 into t square or something. So for any value of t, this will always be 0. So if someone tells you, is the zero vector a vector which is 0 for some values of t, then that is wrong. The zero vector is a vector which is 0 for all values of t. Okay, and now we finally get to have a look at subspaces. So subspaces are the subspace of a vector space is a subset H of V. So basically we define vector space as let me just make some space here, a set of vectors, right? So you had v1, v2, v3 and so on, which satisfied those 10 axioms. So say if you took a set of vectors from this, say vi, vi plus 1, vj, vj minus 1 and so on, then that is a subset of this vector, this set of vectors, right? We are looking at this in the traditional definition of sets, where a subset of a set is just a smaller set which has elements from that larger set. Now a subspace is a subset which follows these three properties. So you can have this subset, but it is not necessary that this subset is a subspace. For it to be a subspace, it must follow these following properties. The first property is the zero vector of V is in H. So basically, if you had, say, this subset, let's say you had this something and so on, let's make them vectors for arguments sake, 2 1, just something like this, and you took this 1 1 and 2 1, then this is a subset of this larger vector set, but this is not a subspace. For this to be a subspace, this zero vector from the larger vector set has to be present in this as well. I hope I got that point across. Next, H is closed under vector addition. So similarly, like we had earlier, if we have two vectors in H, then their sum should also be in H. And similarly, if there is a vector in H, then its scalar multiple should also be in H. Uh, Property A, B, and C, these are the properties guarantee that a subspace H of V is itself a vector space under the vector space operations already defined in V. To verify this, note that properties A, B, and C are axioms 1, 4, and 6 respectively. We can just go up and see that axioms 2, 3, and 7 to 10 are automatically true in H because they apply to all elements of V. So basically this is saving us from work, because when V is a vector space, then all elements of V must be satisfying those axioms. And if they satisfy those axioms, then there is no need to prove that for H as well. Axiom 5 is also true in H because if U is in H, then minus U is in H by property C, because there the scalar C is can be -1, and we know from equation 3 that earlier in the section that minus U is the yeah, that isn't what we need to look at. So every subspace is a vector space. Yeah. Conversely, every vector space is a subspace of itself and possibly of other larger subspaces. So and let's say if you have a vector space and you take all those elements and make an exact copy, then you can say that this is a subset of that set, right? We aren't really dealing with proper and improper subsets. So every vector space is a subspace of itself and possibly of some larger spaces as well. The term subspace is used when at least two vectors are in mind, with one inside the other, and the phrase subspace of V identifies V as the larger space. These are self-explanatory things. Now let's look at a few examples for subspaces as well. The set consisting of only the zero vector in a vector space V is a subspace of V called a zero subspace and written as 0. Okay. Example 7. Let P be the set of all polynomials with real coefficients with operations in P defined as for functions. Then P is a subspace of the space of all real valued functions defined on R. Also, for each n greater than 0, Pn is a subspace of P because Pn is a subset of P that contains a zero polynomial. The sum of two polynomials Pn is also Pn, and scalar is. So basically what they're trying to say is if we take P to be the set of all polynomials, right, with operations in P defined as for functions, then P is a subspace of all the real valued functions defined on R. So if you took a P to be a set of all polynomials with real coefficients, then that is corresponding to taking a subspace of all the real valued functions defined on R. Also, for each n is greater than or equal to 0, Pn is a subspace of P. So say if you had P1, P1 would correspond to the polynomials where the highest degree is 1. So that would be a subspace of P which has all the degrees, right? Now let's look at example 8. The vector space R2 is not a subspace of R3 because R2 is not even a subset of R3. Yeah. So basically the vectors in R3 all have 3 entries, whereas vectors in R2 have only 2. So this is a subset of R3 that looks and acts like R2, although it is logically distinct. Because someone might argue, if you had just say S and T in R2, that the third element can be anything. It is not necessarily 0. But this is sort of a plane. This already has the third element defined as 0, which means that this is a plane which has z is equal to 0. So this is basically the xy plane. So basically if we need to prove that this is a subspace of R3, then we just need to show that those 3 properties, because the 0 vector is evidently inside it. If we took 2 vectors in this plane and added them, that would always give a vector in the same plane, because there is no sum of 2 vectors in a plane which can give the vector in another plane, right? And which can give a vector which is not inside the plane. And finally, if you scale a vector, it will always remain in the same plane. And example 9, a plane in R3 not through the origin is not a space of R3 because the plane does not have the 0 vector. Similarly, a line in R2 not through the origin is not a subspace of R2. It might have been difficult to draw for R3, but for R2 it is evident, because if say you have a line, this line is not a subspace of R2 because this line does not pass through the origin. And I guess this is the last topic in this, a subspace spanned by a set. The term linear combination, we know this, the linear combination refers to sum of scalar multiples of vectors, and span of p vectors denote the sum of all vectors that can be written as linear combination of v1 to vp. So with some weights multiplied, you can have a set of all vectors which can be written as generated from these p vectors. So let's say you have v1 and v2 in a vector space V, and let H denote the span of v1 and v2. Then we need to show that H is a subspace of V. So basically in this figure 9, you had these vectors v1 and v2, and the span of v1 and v2 is this plane, right? And you just need to show that this span is a subspace of the entire vector space. v1 and v2 lie in this x1, x2, x3 coordinate space. There is no need for the coordinate system, but just for convenience sake they've given it. So evidently the zero vector is in there in the span of v1 and v2 as well. The zero vector will be there because the weights can both be zero and giving origin to a zero vector. Secondly, let's say you have two arbitrary vectors s1 v1 plus s2 v2 and t1 v1 plus t2 v2. So you can basically add them and take s1 plus t1 v1 common, giving s1 plus t1 as the coefficient, and similarly s2 plus t2 as coefficient. This is also a linear combination of u plus of v1 and v2, so this will also be in the span. Similarly, if you multiply this with a scalar, this is also a linear combination, so this will also be in the span. Hence we've shown that these are operations are this H is closed under these operations, thus H is a subspace. Finally, we have this last theorem. If v1 to vp are in a vector space, then the span of this is a subspace of V, right? Because the properties which we need to check for are quite similar from here. This can give us a general idea. This can give us a specific idea. If we had v1 to vp here, then if we had taken all the weights to be 0, that would have given rise to the zero vector. If we had not done that, rather we had taken some coefficients like s1 to sp and t1 to tp, then again similarly we could have taken s1 to s1 and t1 common, s2 t2 common, and up till sp tp common. And finally multiplying with some scalar would be equivalent to giving like cs1, cs2 and so on up till csp, and that would have also lied in the same plane, and hence we would have proved that H is closed under scalar multiplication and scalar addition. Also the zero vector is in there, so this would have been a subspace of V. This example, let H be the set of all vectors of the form a minus 3b, b minus a and b. So basically these are the entries of the different rows of the vector, and that is let H be the H be this, and a and b are in R. So we have to show that H is a subspace of R4. So basically you took this a minus 3b, b minus a and b, and you split them. So if you rewrite them, then you know there is a here, a minus a and a 0 times a. So you can rewrite this as something like this. Similarly, if you took b common, you have a minus 3, a 1, a 0 and a 1. So these two vectors v1 and v2 are basically the vectors which span H, and hence this theorem indicates that H is a subspace of R4 by theorem 1. So we don't really need to prove this again and again. By using that theorem we can definitely show that. For example 12, for what values of H will Y be in the subspace of R3 spanned by v1, v2 and v3? So basically if you have v1, v2 and v3 here, the solution there, know that Y is in only if H is 5. The solution is worth reviewing, but let's look at this in another manner. Let's say you want to like rewrite this in some form, so you can just take the vector. You just want to show that this is in the span of these three vectors, right? So let's say you took the coefficients as x1, x2 and x3, and then you can just equate that to this. So you'll get a set of three equations: x1 plus 5x2 minus 3x3 is negative 4, and so on. And you can solve them to show that what value of h will lead to this y being inside that subspace. This what value of h will lead to y being a part of the subspace of R3. I know this video is quite long, but we've exhaustively covered subspace, vector space, and a subspace spanned by a set.